In this video, I'm going to take you through an econometrics quiz on the topic simple linear regression. You have two options to take this course. Either you can directly go to our website eduspread.com and you can take this course over there, or you can go through this course with me in this video right now. I'm putting the link to the quiz in the description of this video in case you want to attempt the quiz on your own. So let's get started. So the first question is, a dependent variable is also known as, well, the right answer is part D, response variable. Okay, now see, this is something that you should know, that your y variable, that is your dependent variable, and your x variable, that is your independent variable, they have different names. For example, y variable has these names, so it can be called explained variable, response variable, predicted variable, or the regressant. So you should be familiar with these different names, as sometimes in an exam they give you a different name. Okay, so just like we have different names for the dependent variable, we also have different names for the independent variable. Okay, for example, one of the names that we have for the independent variable is regressor, right? So you should be familiar with these different names. So the right answer is part number D, response variable. Let's move to the next question. In the equation y equal to beta 1 plus beta 2x plus u, beta 1 is the, well, the right answer is intercept parameter. So beta 1 over here is giving us the intercept, and this is a population equation, so it is a parameter. So that's why the right answer is D, intercept parameter. Let's move to the next question. The term u in the equation y equal to beta 1 plus beta 2x plus u is usually referred to as, well, the right answer is population error or disturbance term. Now see, this is something you need to be really careful with. This over here is a population equation. Okay, so we have population equations as well as we have sample equation. The equation that I have written over here, this is a population equation, and this u is actually your population error, and population error is also called disturbance term. When we talk about the sample error, we can also call them residuals. For sample errors, depending on the textbook that you're working with, you can have different notations. In some textbooks, you will see the notation E. In some textbooks, you will see the notation U hat. So generally speaking, you will see these two notations for the sample errors or the residuals. Over here, this is the population equation. So this is population error or disturbance term, right? So this is your question number 3. Let's move to question number 4. As per the method of OLS, we find the estimators of beta 1 and beta 2 such that the following is minimized. So in the method of OLS, we actually minimize the sum of squared residuals, right? So the right answer is part number D. Let's move to the next question. Consider the following regression model, y equal to beta 1 plus beta 2x plus u. Which of the following is one of the algebraic properties of OLS? First of all, note that you can have different words over here. So in some textbooks, they also write mechanical properties of OLS. In some textbooks, they also write useful results of OLS. Okay, so you can see these terms as well. So algebraic properties of OLS, mechanical properties of OLS, or useful results of OLS. Now let's take a look at the options that are given to us. The part A is the sum, and therefore the sample average of the OLS residuals is positive. So if I use the notation, let's say UI hat for my residuals, the part number A is saying that summation of UI hat is going to be greater than 0 if you work with the method of OLS. Well, this is wrong. Okay. The part number B is the sum of the OLS residuals is negative. So as per the part number B, it's summation of UI hat less than 0. Well, even this is wrong. Okay. Why are these two wrong? Because we know that if we work with the method of OLS for this particular model, we are going to get the sum of the residuals equal to 0. Okay. So this is what we get, right? The summation of UI hat comes out to be equal to 0 if you're working with the method of OLS. This is one of the useful results of OLS. So the first two parts are false. Let's take a look at the part number C. In the part number C, it's written the point x bar comma y bar. So this is x bar comma y bar always lies on the OLS regression line, which can also be called the sample regression line or the line of best fit, where x bar is the sample mean of x and y bar is the sample mean of y. And the part number D is the sample covariance between the x variable and the OLS residuals is positive. First, let's talk about part number D. In part number D, we are saying that the covariance between the x variable, so this COV means covariance, between the x variables and OLS residuals, that is u hat, is greater than 0. Well, this is false because the covariance between x and u hat is equal to 0. Okay, this is also one of the useful results of OLS. The right answer is part number C. Okay, so this question is completely based on the useful results of OLS. A is wrong, B is wrong because summation of u hat is equal to 0. C is the right answer and D is wrong because the covariance between the independent variable and the OLS residuals is actually 0. It is not positive. Okay, in case you are not that familiar with the useful results of OLS, you can take a look at the videos that I have on that. So you can go to our YouTube channel, that is EduSpread. On this channel, you will see this playlist, Econometrics Mathematical Proofs. Okay, this playlist over here. Once you open this playlist, you will see all of these videos over here. And there are these two videos, Useful Results of OLS Part 1 and Useful Results of OLS Part 2. If you take a look at these two videos, then you'll be clear with this question that I have just discussed. Okay, because these things are discussed in these two videos over here. Okay, so you can revise useful results from those two videos. So the right answer is part number C. So let's move to the next question now. Question number 6. Consider the simple linear regression model y equal to beta 1 plus beta 2 x plus u. If we estimate this model using the method of OLS, then the covariance between the estimated errors or residuals and the regressor, that is x, is 0 by construction. Well, we just discussed this. The answer is true. But before I mark this answer, I want you to note a couple of things over here. Note the different terms that we have for the sample errors, right? We can call it estimated errors. We can call it residuals. I can also write the term sample errors. Okay, so these are the different terms that we have. And note one term that we have for the independent variable. This is something that I also told you when we did the first question, that your independent variable x also has different names. So over here, instead of writing the term independent variable, I have actually written the term regressor, right? So you should know what are the different names that we have for the dependent variable as well as the independent variable. And this is something that we just discussed, that the covariance between your u hat and your x is going to be equal to 0 by construction. Okay, this term is also very important because this is not an assumption, right? This is not something that we are assuming. The OLS method is constructed in such a manner that you end up getting this. So this is not an assumption. Okay, so not an assumption. This is something that happens by construction because the OLS method is constructed in such a manner that the covariance between the residuals and your independent variable comes out to be equal to 0, right? So this statement is true. And once again, this is one of the useful results of OLS. So if you want to revise this, you can actually take a look at these videos that I just showed you. Okay, so the right answer is true. Let's move to the next question. Question number 7. For the simple linear regression model y equal to beta 1 plus beta 2 x plus u, the sign of the slope estimator is the same as the sign of the correlation between x and y. Now this question is a really good question. So let's do this step by step. They are saying that this is the simple linear regression model that we have, and they are talking about the sign of the slope estimator. Okay, first of all, let me define a notation for the slope estimator. So let's say the slope estimator is beta 2 hat. Note that this beta 2 over here, this is a parameter because this belongs to the population model. So beta 2 is the slope parameter. Okay, and beta 2 hat is the slope estimator. So first of all, let's take a look at the formula that we have for beta 2 hat. Now, if you have gone through simple linear regression, you should know that there are multiple formulas to calculate beta 2 hat. So one of the formulas which I believe many of you would know is this: summation of xi minus x bar multiplied by yi minus y bar divided by summation of xi minus x bar whole square. Okay, so this is one of the main formulas, so I'm expecting that you know this. Now, how can you work with this formula? See, understand it in this manner. What is the formula to calculate sample covariance between two variables? So the sample covariance between x and y is actually equal to summation of xi minus x bar multiplied by yi minus y bar divided by n minus 1. Okay, so if I cross multiply, I can write summation of xi minus x bar multiplied by yi minus y bar equal to n minus 1, and this is multiplied by sample covariance between x and y. Okay, call this equation 1, right? And what else do we know? We know that what is the variance of x? So what is the formula that we have for variance of x? Variance of x is equal to summation of xi minus x bar whole square divided by n minus 1. Okay, now if I cross multiply, then from here we will get that summation of xi minus x bar whole square is equal to n minus 1 multiplied by variance of x. I'm going to call this equation number 2. Right? Now see, what do we get from equation number 1? This expression is equal to this, and this is the numerator that we have over here. So instead of this numerator, I can actually write n minus 1 multiplied by sample covariance between x and y divided by, I can replace this expression, like take a look at the equation number 2. So summation of xi minus x bar whole square can be written as n minus 1 variance of x. So over here, I can write n minus 1 variance of x. This and this gets cancelled. So that means beta 2 hat can also be written as sample covariance between x and y. So sample covariance between x and y divided by variance of x. Okay, so this is one more formula that you should keep in mind. Now think of it in this manner. They are asking you that what's the relationship between the sign of the slope estimator and the sign of the correlation. Now let's take a look at the formula that we have for the correlation. How do we define correlation between two variables? So correlation between x and y is covariance between x and y divided by standard deviation of x. So s dx multiplied by standard deviation of y. Okay, now we have to compare the sign of beta 2 hat with the sign of correlation, and we have to see that are we able to find any sort of relationship between the sign of these two. Now think of it in this manner. If you take a look at beta 2 hat, what is in the denominator? In the denominator you have variance of x, and variance of x is always a positive thing. Okay, so the denominator cannot be negative. And in the numerator, you have sample covariance of x and y. So whatever the sign of beta 2 hat is, that depends on the sample covariance between x and y. Okay, it's not necessary to write this word sample. I hope you understand this. So I can just call it covariance between x and y. So the thing is that the sign of beta 2 hat, whatever the sign is, it depends. The sign depends on covariance between x and y. Okay, so the sign depends on covariance between x and y. Right, because the denominator is always positive. Similarly, if you take a look at this correlation formula, the denominator is standard deviation of x multiplied by standard deviation of y, and standard deviations are always positive. That means the denominator is always going to be a positive number. Whatever the sign is going to be, it depends completely on the numerator. So the sign of the correlation also depends on this covariance between x and y, and the sign of beta 2 hat also depends on covariance between x and y. So whatever the sign is going to be, it's going to be the same. Because if your covariance between x and y is negative, that means beta 2 hat will have a negative sign, and the correlation will also have a negative sign. If your covariance between x and y is positive, then beta 2 hat will have a positive sign, and even the correlation between x and y will have a positive sign. So both of these, okay, their sign depends on covariance between x and y. So they are always going to have the same sign. Right? And this is what I'm asking in the question over here, that for the simple linear regression model, the sign of the slope estimator is the same as the sign of the correlation between x and y. So the right answer is true. Okay, this is right. Let's move to the next question. Question number 8. R square is TSS divided by ESS. Well, this is a straightforward question, and the right answer is false, because it's not TSS divided by ESS. R square is ESS divided by TSS. Okay, this is one of the formulas for R square. We have one more formula. In fact, we have many formulas, but I'm just going to write another one. We know that TSS is equal to ESS plus RSS. And let me tell you what I mean by these. So TSS means total sum of squares. ESS means explained sum of squares. RSS means residual sum of squares. Okay, in some of your textbooks you will see that they have written SST, SSE and SSR. Even that is fine. It's just that I feel more comfortable with this notation. Okay, so TSS is equal to ESS plus RSS. So this is one of the formulas. Another formula could be that instead of ESS you put TSS minus RSS. So if I replace ESS with TSS minus RSS, then you get one more formula. So this is SS over here, RSS. So this is equal to 1 minus RSS over TSS. Okay, so this is one more formula that we have, right? So R square is equal to ESS divided by TSS, or it can also be written as 1 minus RSS divided by TSS. So the statement that's given over here, that R square is TSS over ESS, this is false. Okay, so I'm going to mark false over here, confirm. And let's move to the next question, that is question number 9. The value of r square, well, the right answer is lies between 0 and 1. Okay, because r square is what? R square is ESS divided by TSS. And think of it in this manner, that what is ESS? ESS is explained sum of squares. Okay, so basically you are squaring something and then you are summing that. So it has to be a positive number. It cannot be negative. It is explained sum of squares. And what is TSS? TSS is total sum of squares. So once again, you are squaring something and then you are adding something. Even this is going to be a positive number. So r square can never be negative because both of these things are positive, right? The second thing is that ESS is less than or equal to TSS. Okay, and this is because TSS is equal to ESS plus RSS. Okay, so this is your total, this is your explained, and this is your residuals. Okay, or you can also say unexplained. Now explained portion has to be less than or equal to total portion, right? So r square is always going to lie between 0 and 1. The maximum value that we can have for r square is 1. Okay, and when will we attain the maximum value? The maximum value will be attained when ESS is equal to TSS. That means RSS is equal to 0. Okay, that would mean that you're able to explain everything. Generally speaking, you will never see this kind of thing happening because you will never be able to explain all of it. So if ESS becomes equal to TSS, then r square becomes 1. That's the highest value that r square can take. And what's the minimum value that r square can take? Well, the minimum value is 0. And that will be achieved when ESS is equal to 0. Okay, right? So when ESS is equal to 0. So ESS either is going to be a positive number. The worst case scenario could be that ESS could also be equal to 0. Okay, ESS equal to 0 would mean that your model is totally pathetic. You're not able to explain anything, right? So r square is going to lie between 0 and 1. That's the right answer. So let's move to the next question now. Question number 10. Y equal to beta 1 plus beta 2x plus u, a null hypothesis that beta 2 equal to 0 states. Well, the right answer is part number B. Beta 2 equal to 0, if that's your null hypothesis, that would mean that x has no effect on the expected value of y. So that's what this null is stating. Okay, so part number B is the right answer. Let's move to the next question. The general T-statistic can be written as what? Well, the general T-statistic can be written as this. Okay, make sure that you understand the difference between C and D. In the part number C, in the denominator, they have the variance. Okay, when we write T, we do not have the variance in the denominator, we have the standard error. So the right answer is part number D. Let's move to the next question. Question number 12. Consider the following null and alternative hypothesis. Null is that beta 2 is equal to 0.16. Alternative is that beta 2 is greater than 0.16. The above setup. Well, this is a straightforward question. Think of it in this manner, that how do we decide that in which tail we are going to put the rejection region? So I'm going to explain you that now. I'm going to tell you a trick so that you could remember it properly. Well, the thing is that if you want to see that in which tail the rejection region is going to lie, you have to take a look at the alternative hypothesis. Okay, it all depends on the alternative hypothesis. If your alternative hypothesis is something like this, if it's beta 2 not equal to 0.16, right, then the rejection region is going to lie in both the tails because it's not equal to. So it's going to become two-tailed then. Okay, it's going to become two-tailed, right? However, if it's not this, then there are two options. Either it could be beta 2 greater than 0.16, right? That could be your alternative, or your alternative could be beta 2 less than 0.16. Okay, so these two cases are the cases of one tail, because in these two cases you're only going to have the rejection region in one of the tails. Now, how do we remember that in which tail are we going to put the rejection region? See, when you have a greater than sign, you try to create an arrow. Okay, if you try to create an arrow over here, then the arrow will point towards the right. Okay, that means the rejection region is going to be over here in the right tail. Okay, over here, if you have a less than sign and if you try to convert this into an arrow, then the arrow will point towards the left. That means the rejection region is going to be over here in the left tail. Okay, so this is how you can keep this in mind. In our case, the alternative hypothesis is beta 2 greater than 0.16. So if I try to create an arrow over here, the arrow will point towards the right. This is a one tail test and we are going to have the rejection region in the right tail. So that means this setup indicates a one tail test with a rejection region in the right tail. So the right answer is part A. Let's move to the next question. The error term in a regression equation is said to exhibit homoscedasticity. So basically, they are asking you the definition of homoscedasticity. Part number A is it has zero conditional mean. Part number B is it has the same variance for all values of the x variable. Now see, this is also one of the terms that we have for the x variable. So we can have independent variable, we can have regressor, we can have this. I'm saying this again and again. You should be familiar with all these terms. So you can also call it independent variable, or you can also call it regressor. Okay, so there are multiple terms and you should know all of these terms. So now which of these is right? And by the way, by this it we mean the error term. Okay, so the right answer is going to be part number B, when it has the same variance for all values of the x variable. Okay, this is how you define homoscedasticity. This is the definition of homoscedasticity. So part number B is the right answer. Let's move to the next question. Question number 14th. Which of the following assumptions is not necessary for OLS estimators to be unbiased? Now this is a good question. See, when you read simple linear regression, you must have gone through multiple assumptions, okay? And you must have gone through the Gauss-Markov theorem as well, which says that the OLS estimators are blue, given that these assumptions are satisfied. Now, one of the things that you should be really careful with is that which assumption is required for which part. For example, if we want our OLS estimators, that is, let's say beta 1 hat and beta 2 hat, if we want them to be unbiased, okay, then do we need all the assumptions? Like, do we need the assumption of homoscedasticity, zero conditional mean, and all the other assumptions? Do we need all of them for OLS estimators to be unbiased? Well, the answer is no. Okay, if you want your OLS estimators to be unbiased, like only unbiased, then the assumption that you need is this: zero conditional mean of the error term. Homoscedasticity has nothing to do with unbiasedness. Okay, whether the homoscedasticity holds or does not hold, the unbiasedness property is not affected. So basically the unbiasedness part depends on this assumption and it has nothing to do with this assumption. So even if you have heteroscedasticity, okay, so even if you have heteroscedasticity, if this assumption is satisfied, OLS estimators are still going to be unbiased. Okay, so whether homoscedasticity, heteroscedasticity, doesn't matter. Unbiasedness property does not get affected till the time this assumption is satisfied. Okay, be careful with this. This is something which I have also discussed in my videos. So once again, if you go to this playlist, you will see certain videos over here. So for this, you can take a look at this video, Gauss-Markov theorem explained. So I've talked about the Gauss-Markov theorem in detail over here with all the proofs. If you take a look at this Gauss-Markov theorem explained, I have talked about which assumptions are required for which part. This is something that you really need to be careful about. Okay, so this was question number 14th. The right answer is, well, the right answer is not part number B. The right answer is part number A. They are asking us which of the following assumptions is not necessary. Okay, so when they are saying is not necessary, we know this is necessary, this is not necessary. Okay, so when you have to select the answer, we are going to select part number A. So now let's move to the next question. This is the last question that we have. They are asking us which of the following conditions is not necessary. Okay, once again, not necessary for OLS estimators to be blue. Well, the right answer is part number A. That is, all the errors are normally distributed. See, this is the assumption that you do not need for OLS estimators to be blue. If you do not need this assumption for OLS estimators to be blue, then what is the importance of this assumption? Well, this assumption mostly helps you in hypothesis testing. Okay, so this helps you with the hypothesis testing. How does this assumption help you with the hypothesis testing? Well, if you want to do hypothesis testing, you need to have some knowledge related to the distribution of the estimators. And by estimators, I mean your beta 1 hat and beta 2 hat. And if you take this assumption helps us in finding the distribution of those estimators. Okay, and you know, this assumption is not even necessary. If you have a large enough sample size, then you can just work without this assumption. But even if you are taking this assumption, this is not to make sure that OLS estimators remain blue. The only importance this assumption has is in the hypothesis testing part. Okay, so the right answer is going to be part number A. This assumption is not necessary for OLS estimators to be blue. And let's confirm the answer. And that's it. We are done with the quiz. So in total, we discussed 15 questions over here. How many of these questions did you get right? Let me know in the comment section. And if you have any confusion in any of these questions, if you do not understand the concept, let me know in the comment section and I will reply if there is any confusion. Okay, so that's it for this video.